The title of this presentation is Algebraic Characteristics of the Six-Vertex Model, Coloring Double Grothendieck Polynomials in Yang-Baxter. To begin with the presentation overview, we'll be further developing upon notions from previous presentations, in addition to drawing connections between double Grothendieck polynomials and the partition function of the six-vertex model. And in formulating such connections, we draw upon notions from K-theory, which can be discussed insofar as to highlight additional characteristics of the 20-vertex model over 3 dimensions that are connected and that we can further develop in light of the quantum inverse scattering type methods in 2 and 3 dimensions. And we'll have to do this by drawing the attention of the viewer to some previous discussions of the potential connections of interest from such algebraic properties of the 20-vertex model and how more the algebraic properties from the representation theory and the construction of the universal R matrix also come into play. So from previous presentations, like we have been mentioning, we introduced research areas within statistical mechanics, broadly speaking, which are related to some previous works on crossing probabilities and Russell-Seymour-Welch, the localization of the height function for vertex models, integrability from the quantum inverse scattering method. And we were exhibiting connections between all the areas mentioned above with the notions of integrability of color vertex models, which shares connections with representation theory, algebraic combinatorics, and algebraic geometry. So in the previous talks, we were more looking from a computational point of view of making use of the Poisson bracket and carrying out several computations with the Poisson bracket in looking at how the entries which come into play from our computations with the Poisson bracket, they can either involve some power of the sine of 2 eta term, as well as from the fact that the other terms can come from individual entries which are parameterized in the transfer matrix. And moreover, that we can introduce some simplification to some of the Poisson brackets when one of the argument is dependent upon a u and another argument is dependent upon another parameter, u prime. And that allows us to obtain some type of asymptotic expression from these entries, which are relating to the entries that the transfer matrix would satisfy approximately in the large n limit as we obtain the quantum monodromy matrix over an entire space in infinite volume. So this is going to be much looking at a little bit of a different perspective, but it's still important for us to keep in mind how those previous objects were defined and described and how they can still come into play and have connections with some of the more algebraic or geometric or combinatorial objects, which we're going to be discussing more in this presentation of the series from one reference. And so like we have been mentioning, the quantum inverse scattering method really takes advantage of the fact that in the presence of inhomogeneities, the six-vertex model can be shown to possess certain integrability properties by adapting the quantum inverse scattering approach. And we've been discussing about how the three-dimensional case of the quantum inverse scattering approach relates to the structures of the L operators, which hold up to Dynkin isomorphism. So there's actually a class of these L operators which come into play. And taking the product of these L operators is helpful for looking at the quantum monodromy and the transfer matrices. And this is relating to more classical uses of the beta ansatz and the transfer matrices and various expressions for the eigenvalues or other types of related quantities from solutions of the beta equations, because it's looking at different types of characteristics and it's seeing which properties and characteristics of the argument would not hold as we pass to the higher dimensional space, where these entries of the L operator, they have various algebraic interpretations, which we have been mentioning over the past couple of presentations, like the last presentation or two. And so the Ising model, it shows connections with several other models arising from statistical mechanics. And this is just to reiterate some of the previous examples and characteristics of the model that we can have in mind. For example, from the logarithmic delocalization paper for the six-vertex height function, we established some type of continuity and look at different perspectives of an argument for crossing probabilities in Russell-Seymour-Welch, which was originally developed by Dumino-Copan, Carilla, Manulescu, and Olamara. And then for the Poisson structure paper, which is looking at more the mathematical physics side of things rather than just the crossing probabilities in Russell-Seymour-Welch side of things, is the fact that from the paper from Keating, Reshetikhin, and Sridhar, in the last sentence of their paper, they draw attention to being able to make use of some quantum inverse scattering type approaches from the seminal reference from Faddeev and Tahatan, and how this can be manipulated, or not manipulated, but we can further adapt it to perform some similar type of manipulations with the Poisson bracket that they draw our attention to. And then even in the last reference that's given for open boundary conditions of the higher rank D23 spin chain in sectors of conformal field theories, it's very much a more narrow application of the beta ansatz and the beta root type approach to look at the density of roots of the beta equation and to form some type of interpretation about the sectors of conformal field theories and the behaviors from the Hamiltonian or from the transfer matrix, and ultimately other types of Hamiltonians, which we can obtain from a logarithmic derivative of the transfer matrix, how that can result in some types of interpretations from the conformal field theory point of view. And these other four papers, like we've been talking about here, they look at other types of ways in which disorder or either order can be enforced in different types of models, and how we can look at various statistical measurements or measures or quantifications to try to get an idea of which type of region of the phase diagram we're located in particular, whether the phase transition could be sharp or not. And so when we had introduced the six vertex model, we didn't necessarily initially draw so much attention to the higher dimensional three-dimensional six vertex model, i.e. the 20-dimensional vertex model on the triangular lattice. But this is just to reproduce the type of configurations, the type of configurations that we can have under this model. And we can introduce the height function, which is given by graph homomorphism, which is from the faces of the torus or the faces of the square lattice into the integers, given the stipulation that the height function only goes up or down by one for each arrow that it crosses. And then we can introduce an isotropic parameter choice for these weights. And then we can form from the isotropic parameter choice a weight which we normalize in the partition function of the torus. And this is important to define a probability measure and an expectation, as well as a bounds probability measure and a bounds expectation that are both supported over the torus, resulting from the fact that the logarithmic delocalization result, it holds over when the probability measure and the expectation are supported over the torus. And as we had been mentioning, but very briefly to reiterate, which will have the connection with coloring of the vertex model, we looked at different variants of the vertex model, whether it be the lower rank D22 spin chain, which has 38 possible configurations. And this is described more in depth in one of the preprints that I referenced a couple slides ago, in which it has exact reference in which the authors provided each one of the 38 configurations in the sample space, as well as drawing our attention to the fact that the first six configurations, because it's a degeneration, the D22 spin chain, the lower rank spin chain is a degeneration of the ice rule that's satisfied by the six vertex model. The fact that the first six configurations are the same, but then we have a bunch of different other configurations within the 32 other configurations within the sample space, which some of which don't have four arrows orientations assigned to all the four arrows, like we see 7 and 8. They have orientations only assigned to two of the arrows, or there can even be different types of configurations like 9 through 14, in which you can introduce some coloring of the edges if they don't have some orientation that's already imposed on them. And the Yang-Baxter equation comes into play for the lower rank spin chain and the higher rank D23 spin chain, from the fact that we can take some Jimbo matrix, which is just some 3x3 matrix, and we can perform this exponential transformation of every one of the entries of the Jimbo matrix. And then the R matrix that we obtained from rescaling and transforming the Jimbo matrix satisfies Yang-Baxter. And we had already described a lot in terms of what the Yang-Baxter equation implies, namely the quality of the partition of two partition functions for the six vertex model, and it's relating as an intertwining relation. Now, also part of the fact why I deliberately brought up as a brief reiteration of the previous presentations, the Yang-Baxter equation, because there can be more of a connection between double Grothendieck polynomials that I didn't emphasize, which can be relating to potentially some type of geometric interpretation, which isn't exactly inherent, or which isn't exactly present in the matrices which satisfied the Yang-Baxter equation in the uncolored case. So in the colored case, we can again observe that there will be some broader type of algebraic interpretation that we didn't have that was present either in the presence of inhomogeneities or in the absence of inhomogeneities for the six vertex model, and how having this type of interpretation is going to give us more of a broad idea about how the representation theory and the combinatorics and possibly the geometry can come together from the probabilistic perspective of what we had introduced originally the six vertex model as, namely some type of square ice model, or it can either be a three-dimensional ice model that has some interpretation depending upon hydrogen and oxygen configurations which are residing over the plane. In the higher rank transfer matrix, which we had for the D22 spin chain, is given by the fact that the state space for forming the configurations in the higher rank transfer matrix is given by 36 possible configurations from the tensor product from these six ket states with itself. And we can denote for brevity just T of open, namely the open transfer matrix under open boundary conditions, as just boldface T open of U. So we just dropped this notation, which exhibits that this is the form and characteristics of the total number of spaces which belong in the state space for the transfer matrix, as well as just that's a type of object, how we signify and manipulate it in that reference that we've been referring to. And under open boundary conditions, we can pour the transfer matrix by taking two products of R matrices as well as two other products of K matrices for respectively enforcing the boundary conditions of the chain at the left and rightmost endpoints of interaction. And now with a short review of the materials that are presented in the previous part, we can provide now like a type of overview, another overview of the forthcoming material in this part, in which we distinguish further between colored and uncolored vertex models, and we discuss challenges to solutions of the Yang-Baxter equations of R matrices encoding the boundary conditions and the like. And this will overall help us exhibit how several algebraic objects relating to the six vertex model ultimately rely on the symmetric group. So we'll demonstrate how these objects all share in properties and qualities and very basic objects that are defined in the symmetric group, and how having this group, it really relates to a connection with the partition function of the model, which would be interested because for discussing the connection between the partition function and of the six vertex model and the double Grothendieck polynomial, the colored R matrices will come into play, and they have a very similar type of interpretation and visual way to represent these states in a sample space over a finite volume, which very much relates to and builds on previous types of ideas that we talked about from connectivity events and connectivity properties of the crossing of the height function. It's just that it's a crossing of a colored height function. And then there are additional characteristics we can impose on top of this coloring condition. And so to further study models within integrable probability at the interface of representation theory, algebraic geometry, and combinatorics, we will discuss the coloring of the vertex models, reintroduce the objects like we had previously discussed. We already introduced them, relating to the analysis of the beta equations, which were discussed in the first part of the video. So that material, we pretty much already reiterated that, you can look at different classes of boundary conditions, either for a lower rank or a higher rank spin chain. And the fact that you can formulate a transfer matrix and look at the density of the roots of the beta equations and formulate a local Hamiltonian from the logarithmic derivative of the transfer matrix is just relating very much to the integrability of the Hamiltonian flow for the inhomogeneous six vertex model and computations with the Poisson bracket for determining and having an idea about some type of Poisson structure that the six vertex model satisfies under inhomogeneities. And this can help us contemplate on how further, in some other more algebraic terms, how notions of integrability for an uncolored vertex model can be used to study notions of integrability for colored vertex models. And this will help us determine whether any notions of universality can be recovered from classes of vertex models, i.e. how many possible configurations are allowed in each sample space, as well as connections with stochasticity and coloring. And so to begin answering some questions and further describe these types of topics, we introduce objects which are defined in the following type of paper, which I'd kind of been alluding to throughout other parts of the presentation, namely the reference double Grothendieck polynomials and colored lattice models, by Buchiumas and Shrimshaw. So these authors together really define and make rigorous the types of connections which we had mentioned, which we can first mention to further build upon the connections with the other types of objects which we had introduced for the quantum inverse scattering type of method in the previous presentations, as well as from the fact that having these types of characteristics in mind, it can give us more of an algebraic flavor and an algebraic perspective of things, which was probably really, it can be unexpected and surprising just from looking at a double Grothendieck polynomial and being able to formulate some type of connection with the partition function of the six-vertex model and how that relates to coloring the objects that we had used for the quantum inverse scattering type approach. And so broadly speaking, this paper is occupied with examining connections between the double Grothendieck polynomials and the partition function of the colored six-vertex model, like we have been mentioning. And they're also interested in analyzing colored R matrices, much like the uncolored R matrices, which were introduced in the previous works for establishing integrability conditions of the Hamiltonian flow. And it's also relating to statements of the Yang-Baxter equation, and as well as finally combinatorics of the semi-standard Young tableau. And so this is one figure that's given from their paper that I've directly reproduced as figure 8 because it directly draws connections with types of more probability-centric analyses of the six-vertex model, given from the fact that you can act some type of connectivity event for the crossing of the height function across some strip or some finite volume. And this was useful for establishing, as in the work of Dumino, Copan, Carrillo, Manulescu, and Ulamara, some type of logarithmic delocalization result in which the variance of the height function of the six-vertex model does not grow too fast as the support of the variance is taken to exhaust the whole square lattice over the two-dimensional space that we're looking at for the six-vertex model. And this is very much demonstrating how you can look at this type of idea for constructing a colored six-vertex configuration, where the coloring, before we define it more rigorously and precisely, is given by the fact that we can think about having different types of possible configurations. So we're broadening the sample space while maintaining the ice roll the same. But we're introducing a modification to the sample space of the six-vertex model from the fact that we're looking at either, as we can see here, green or blue or red colors or any other countably many collection of colors that we can color for each one of the edges and the vertices. And we're looking at whether there could be a path, a connected component of one color or single color that stretches across the lattice. So even though this paper from the algebraic perspective and the double Grothendieck polynomials that they talk about and mention as a connection with the partition function of the colored six-vertex model, it's still very much related to a lot of the types of ideas which you look for in formulating some type of crossing probability estimates, or more generally, sampling some type of configuration and looking at its more macroscopic or microscopic characteristics, because we can see even for this configuration in the colored six-vertex model, there can be different ways, obviously, in which as we see one connected component from figure 8 of the paper, their Buchimas and Shrimshaw's paper demonstrates one connected component that has a different length than another connected component of the same color that appears in the left figure but not in the right figure, and so on and so forth. So there can be several different qualities in how we could look at the probability of obtaining or sampling some type of large connected component, or a macroscopic or a microscopic connected component in one color. And so they also provide several expressions for the colored Boltzmann weights. So this is given by the fact that you can look at enforcing different configurations or different arrangements of colors in each one of the configurations, like we see in configuration A2. This has a Boltzmann weight of 1, while two other Boltzmann weight, which are given for the color vertex model, are expressed in terms of, of a direct sum of the arguments x and y. And this also draws our attention to the fact that when you introduce coloring in a vertex model, again, before we've defined anything more rigorously, rather than looking at some qualitative features of the colored vertex configurations for the six-vertex model, the fact that you can have different ways to also interchange or interpolate between colors in a configuration, which will have some type of influence on the Boltzmann weight, as well as on whatever hierarchy of coloring you enforce for your model. Okay, and then the authors of this reference for the double Grothendieck polynomials, they make a connection between the extended lasso and the double Grothendieck polynomials, because they write the Stanislas polynomial as a z term, which is script g, which is just some term that's relating to the Grothendieck polynomials, as well as two arguments x and y relating to the spatial positions, as well as some parameter beta. And just to be clear, this beta is not the same as the inverse temperature, which appears in the Eason model, which we had defined more near the beginning of the series. This is relating to a beta, which is another parameter which will come in the expression for the double Grothendieck polynomials, because you're taking beta and you're raising it to some semi-standard Young tableau. So it's very much a different type of object, which is used to define a polynomial rather than some types of interactions at inverse temperature and a probability measure from a classical model of statistical mechanics. And this is given by the fact that already the double Grothendieck, the fact that the Grothendieck polynomials are double is coming from the fact that you're taking a product over I, where this x sub I term is in the product, but you're also taking a direct sum of each of the x sub i's with a y, and you're raising it to the lambda sub I, as well as multiplying it by an appropriate weight, which is a prefactor to this product over I. So it's just demonstrating how already the fact that as we have mentioned, the fact that the Grothendieck polynomials are double Grothendieck polynomials comes from this feature of the the extended Lasso polynomials, which are given by a direct sum of the x sub I terms over all I, as well as a y term, a y variable. And as we had mentioned, it's important to keep in mind the Yang-Baxter equations, because the Yang-Baxter equations, of course, they're going to have some type of analog and some type of influence in the argument for the vertex models under coloring, given by the fact that from figure 3, another figure directly adapted from the reference, they further reinforce some type of other algebraic interpretation or algebraic characteristic of the Yang-Baxter equation, because you can have some feature of the graph which is given by this crossing at x sub I and x sub I plus 1, and then you can push this feature from the Yang-Baxter equation throughout the whole infinite volume, and until it coincides with those two colored vertices, di plus 1 and dr, which are respectively colored in red and blue. So from the statement of the Yang-Baxter equation for a colored vertex model, it's saying, again, it's asserting the equality of the partition functions for two models, and they specify, Buchemash and Trimshaw, they specify how the boundary conditions can be dependent upon lying within a certain range of colors for the 6-vertex model under coloring. So it's any colors that are within this color gradient that they use for defining the model in the first place. And so the double Grothendieck polynomial comes into play, like how we have been mentioning, is that it's given by the fact that it's given by some quantity g, w of w naught of x, y, and beta. So this beta and x, y arguments also come into play, where we're looking at w naught being some permutation of the symmetric group. So the symmetric group, like we have mentioned earlier, it's coming directly into play because we need symmetric groups and we need permutations to define these types of polynomials in the first place. And it's demonstrating a connection between a standard Lasso, like we had mentioned, and double Grothendieck polynomials. And it's a recursive relation because we define some product for x and y, x and I less than or equal to n. And as we had mentioned, as what appears in the extended Lasso polynomial and also in the double Grothendieck polynomials, that we're taking the direct sum, which is making this Grothendieck polynomial a double Grothendieck polynomial of xi and yi. And then we can define it by taking some type of finite difference operator, some difference operator, which we'll define in the K-theoretic sense a little bit later in the presentation, and also to just demonstrate how that very much relates to other characteristics of the symmetric group, and how the recursive definition is also relating to other permutations of the symmetric group, because we're defining the length of w of s sub I to be the length of w plus 1. So we're having a hierarchy of words of the symmetric group, which are increasing in length one at a time. And then we can define the double Grothendieck polynomial in terms of some type of recursive relation. So it's already demonstrating, as we have been mentioning a little bit earlier in the presentation, how the coloring aspect, it will preserve some types of structures which appear in these models and in these vertex or ice models, but it'll also have some other characteristics and properties, whether it be algebraic, combinatorial, or geometric, and how we can begin already to formulate these things with just permutations from the symmetric group. And so we also had introduced, like we had mentioned, tableau combinatorics, in which from their paper, although this is just a very basic definition that's seen everywhere, in which we're looking at they did the authors Shrimshaw and Buchamas in their double Grothendieck polynomial draw attention to the fact that you can also have, rather than just integer value tableau, also set value tableau, namely in which you put sets in A, B, and C, and it can have a certain shape lambda. So it's describing what are the total number of rows and the total number of columns in this semi-standard or the set valued Young tableau. And then we can fill the boxes of lambda with non-empty finite subsets of 1 or 2 up to n that are weakly increasing across rows and strictly increasing across columns. So they provide a condition for how the items that they put in the set value tableau, it relates to the construction of these polynomials of interest first over semi-standard Young tableau, in which you're just looking at putting numbers instead of sets in each one of the positions and boxes in the tableau. And so from the set value tableau, they can define, they introduce from following another reference, which they make use of the factorial Grothendieck polynomial, given by the fact that it's very similarly defined in terms of as the previous Grothendieck polynomial, but it's different because we're looking at lambda and we want to take partitions of lambda. So lambda is just some number, as well as given from the fact that there's a little bit different notation for the parameters x, y, and beta, in the fact that we still have this beta term, which appears like how I had alluded to earlier in the presentation. You're taking beta, which is some parameter, not to be confused with the inverse temperature of the Ising model that we had talked about earlier, but that it's just some value, some factor, which appears in the summation, and you raise this to t, which is a set value tableau as shape lambda. And then you take a product from each one of the two terms, the two variables that you're taking the double sum from for the Grothendieck polynomial. So this is demonstrating how we started from extended polynomial, we established an equivalence with the double Grothendieck polynomial, and then when we transition from integer value tableau to set value tableau, the fact that the summation here has a set value tableau shape lambda is given in terms of it's given in terms of a factorial Grothendieck polynomial. And there's also flagged factorial Grothendieck polynomial, in which we can introduce further modifications to the set value tableau shape lambda, as well as introducing a flagging on the set value tableau to obtain a different type of Grothendieck polynomial instead of flagged factorial, instead of just a factorial Grothendieck polynomial. And the discrete difference operator is given by the fact that we can take x and y belonging to some space in which we can formulate a direct sum, an expression for the direct sum as x plus y plus beta xy. And then if we take some polynomial or some suitable function in the ring of polynomials with integer coefficients, they introduce the ith Newton divided difference operator in terms of delta I of f in terms of f minus s sub I, or s sub I of f, as well as dividing by some normalization x sub I minus x sub I plus 1. And so, as we had alluded to much earlier in the presentation, there's a k-theoretic version of this difference operator. So this is coming into play from the recursive definition of the double Grothendieck polynomials, and furthermore, how this recursion definition from the length of words of the symmetric group of the double Grothendieck polynomials, it plays a role in defining the double Grothendieck polynomials for either set value tableau or flagged set value tableau, without necessarily going into precise definitions of those topics, of those objects, just demonstrating that once you impose some type of different conditions, this is influencing the power that you raise the beta parameter to, which appears on the summation of the product from those direct sum of those two terms from the most simple double Grothendieck polynomial, let alone which also appears in the flagged Grothendieck polynomial and the flagged factorial Grothendieck polynomials. And so this is demonstrating, as we had alluded to, that the k-theoretic divided difference operator is given by what we use to define the recursive definition from lengths of words of the symmetric group and how this relates to the Grothendieck polynomials, which just coincide and reduces to the ordinary partial differential operator applied to 1 plus beta x sub I of f. So it's just saying the curly d of sub I of f is just set the same as the ordinary differential operator with some additional factor depending upon beta and x sub I plus 1 in front of it. And then we can form a similar type of difference operator given by the fact that the difference has the same type of normalization, namely x sub I minus x sub I plus 1. And then we take the first factor and multiply it by the same term, 1 plus beta x sub I plus 1. but then we also introduce the same, a little bit of a different factor in front of the second factor, S sub I of f, namely 1 plus beta of x sub I. And so at the broadest level, like we have been alluding to and mentioning several times, the symmetric group underlies the construction of the double Grothendieck polynomials, because as they mentioned in their paper, just as a very brief review of the symmetric group, is that we let S sub n, as they mentioned, denote the symmetric or permutation group on n elements. And then for any word in the symmetric group, we can use L sub w to denote the length of the word of w, which is namely the minimum number of transpositions that you need to get to write out the whole word in the symmetric group. And they define a diagram of a word in the symmetric group as being the pairs p and q, which belong to a cross product of 1 by n with itself, where the word of p is greater than q, as well as the fact that the inverse word to q is greater than p. So it's demonstrating how these basic properties, as we have been mentioning of the symmetric group, it's coming into play for the double Grothendieck polynomials, and it's having a very unexpected type of connection with the partition function of the color vertex model. So that's demonstrating how the coloring is coming into play for the vertex model. And so rather than the fact that the coloring holds, this also implies additional similarities, which we wouldn't be sure of exactly whether the Yang-Baxter equation or other parts of the structure are going to hold for the types of L operators like we had mentioned for the 6-vertex model in the 3-dimensional case, which are holding up to Dynkin automorphism. So this is at least demonstrating that at least the coloring, it behaves and it plays nicely with respect to integrability and some other properties, which we could maybe expect to show non-trivially hold. And so like we have been mentioning, from the underlying symmetric group, we can now begin thinking about the potential connections with the material discussed in the previous presentations of the series on the QISM type approaches, in which we had also drawn, as we had mentioned, many types of connections between the lower and higher ring spin chains, and how depending upon the approach that you want to look at, making use of the beta ansatz and in statements and expressions and quantities relating to the beta equations can help you establish some type of integrability condition, which can be a strong type of condition. But it's a difference because a lot of types of proofs on integrability previously, they didn't establish that some type of desirable integrability property of the 6-vertex model holds from either Poisson structure or some information from integrability of the limit shape. So this is demonstrating how sometimes you have to incorporate some additional types of assumptions which can come into play from the coloring of the R matrix and the coloring of the vertex model, and how the fact that the colored R matrix satisfying the Yang-Baxter equation also lends itself to several types of properties from algebraic geometry or other types of symmetric functions, because these polynomials, double Grothendieck polynomials, which relate to the colored 6-vertex partition function, can be thought of as also having their own type of geometric personality and geometric characteristics, and how whether from the QISM type approach we have been mentioning, whether there can be any type of leverage that we can gain in that. And this is just to say that this is all relating from the most basic model which we had considered without the presence of coloring, just the uncolored 6-vertex model, in which from these 6 possible configurations, we can introduce of and make use of similar characteristics and properties of the Yang-Baxter equation from the coloring of these 2 types of configurations. So what's important with the coloring, which we'll also demonstrate, is that if you're introducing a coloring aspect for the 2-dimensional or 3-dimensional 6-vertex model, there can be ways in which the colors can either interface with a quantum zipper argument or interface with some type of transformation of portions of the configuration, which can correspond to connected components of different colors, like we had mentioned from the double Grothendieck polynomial reference. And so the concluding remarks that we have are that we changed the directions of our discussion to more algebraic characteristics of the 6-vertex model, in addition to how the presence of coloring implies a connection between the partition function and the Grothendieck polynomial. And in doing this, we introduce expressions for double Grothendieck polynomials, as well as connections with objects from QISM type arguments. and we began to juxtapose at a more broad level different types of characteristics between these objects. And so this can help us begin to think about how there would be any type of interpretation or feedback from one type of area, namely maybe more of an algebraic perspective, and how that could be used to maybe feed into some notions or to develop some notions of integrability from this. And it's more of just trying to, maybe it could be to establish that some type of common integrability property holds amongst some classes of models, which could be related to some type of universality result. Also from the fact that it can be helpful to determine whether some type of similar condition can be shown to hold in one model if we change the assumptions of the proof and we remove the assumption that there's some type of maybe integrability of the limit shape, or remove some type of other strong assumption which could really prohibit or really strongly dictate the type of behavior of the model that we're expecting to see. Because, like we have mentioned in other presentations, there's a difference between the thermodynamic behavior of the six vertex model and the ferroelectric and anti-ferroelectric regions, which could be interesting, to actually determine whether or how certain arguments might hold or break down in different regions of that conjectured phase diagram. And so this is to say that in the next presentation, we'll describe further how algebraic connections can be developed more. And thanks for watching.